Hello everyone, welcome back. We are in week 4 of this course on reinforced concrete design and this is our second lecture. In this week, we cover column design, right? And we have already discussed the design of column in the previous lecture, and if you recall, we talked about different codal provisions for the design of column. Column can have different cross sections. For example, as you can see here, a rectangular cross section, and then it carries axial load. Actually, we can have three different problem statements. The first one, you have axial load only. Then second option, axial load plus uniaxial bending. And then most general case, axial load plus biaxial bending. Now in this week, we are going to cover axial load only. So for this problem statement, we have a column which is a compression member and it carries a axial load of P. And for that, again, it is made of RCC. That means we have concrete and steel. And if you recall, what are the design steps? First, we need to fix the L effective. For that, we first need to find out the clear length of the column, and then based on boundary conditions, we evaluate L effective. Then once we find out L effective, then we find out L effective by D, which is the least lateral dimension, and based on that, we select whether we have short column or we have any other option. For the time being, we are talking about short column. And we discuss the limit of this L effective by D, for which we actually consider it to be a short column. Now, once that is done, even for this load, as you can see, which is acting at the center, we have to design this column for a minimum level of eccentricity. So E minimum is equal to L by 500 plus D by 30, subjected to a minimum value of 20 millimeter. Now, if this E minimum is less than 0.05 D, then we have special recommendation. Otherwise, we have P ultimate is equal to alpha C times FC, or we can write it, this is FCK, and then AC plus alpha S Fy times AS. So this value of alpha C is 0.446 FCK times AC plus, for steel it is 0.87 Fy times AS. So that is the capacity of the section, where we have contribution from concrete and contribution from steel. Now, obviously, if we satisfy this condition, then we can improve this expression for capacity to 0.4 FCK AC plus 0.67 FYS. Now, this value of alpha S Depends on the type of steel that we use, but in IS 456, we can use this value of 0.87. And for a design problem, we start with, say, D and B, and then first we provide the minimum eccentricity, and for that we check this condition, and then make sure that which formula out of these two possibilities. So this is equation number 1 and this is equation number 2, which expression we are going to use, and accordingly we find out the capacity. So the minimum eccentricity is provided in this case on either side of the column along X and along Y, and accordingly we design. So let us take an example and let us see how we can design these columns. Now, once we design, then we need to provide a minimum number of bars. For rectangular section, we have to have 4 bars, as you can see in this schematic diagram. And for circular cross section, we have to provide at least 6 bars. And these pink bars, they are longitudinal bars, and then we have ties here, lateral ties. And for that lateral ties, again, there are certain guidelines that we need to follow, which we have discussed in the previous class. So their spacing and minimum diameter requirement, all these are defined. Okay. Now, with that background, let us take an example. So our example 1 is design a short column. Its size is 500 millimeter by 500 millimeter for a service load, compressive service load of 3000 kilonewton. Use M30 concrete and Fe 415 bars. Okay, so let us start the design. So what we have here in this given problem is FCK equal to 30 Newton per millimeter square. If Y is equal to 415 Newton per millimeter square, then P service load is equal to 3000 kilonewton. So P ultimate, we have to apply a load factor, which is 1.5 times 3000. So it is 4500 kilonewton. Now, our first check is, point 0.05 D is equal to 0.05 into 500. So it is equal to 25. Right. So recall E minimum is 20 millimeter. Right. Now, what we do, we first find out AG, that is the gross cross-sectional area. So for that, what we have to do, 500 into 500, this is equal to 25 into 10 to the power 4 millimeter square. So that is the second step. Now, once we evaluate this, because we have checked this condition, next step is to find out the steel requirement. So for that, step 3 is Pu is equal to 0.4 FCK times AC plus 0.67 Fy times As. Now Ag, that is the gross cross-sectional area, is summation of AC and As. So what we have here is 4500 into 10 to the power 3 is equal to 0.4 times, we have M30 concrete, so this is 30. Then we have Ag, which is 25 into 10 to the power 4 minus As, that is the area of steel, plus 0.67 times 415 times As. Now in this equation you can see we have only one unknown, and that is the area of steel required. So let us simplify this expression. Here if you multiply 0.4 with 30 and then 25 into 10 to the power 4, we have 3000 into 10 to the power 3 minus 12 As plus, if you multiply 0.67 with 415, we have 278.05. Let us not consider that. So now we can solve for As. So we have 266 As is equal to 1500 into 10 to the power 3. Then ultimately we have As is equal to 1500 into 10 to the power 3 divided by 226, and this is 5639 millimeters square. So first thing we have to check percentage steel, which is As by Ag times 100. So we have 5639 divided by 25 into 10 to the power 4 into 100. And this is 2.25%. So you can see it is more than the minimum steel requirement, that is 0.8% if you recall, and it is less than the maximum allowable steel in column, which is originally 6% in codal provisions, but we do not recommend more than 4%. So it satisfies that criteria. So the percentage of steel is okay. We can now design the bar. So let us try with Phi 25, that is 25 millimeter diameter bar, which is again more than the requirement, minimum requirement, and the number of bars is equal to 5639 divided by pi by 4 times 25 square. So this is equal to 11.59. So provide 12 phi 25. So that is the steel designed for this column. Now we'll go for detailing, but before that, we also have to check for lateral ties, right? So lateral ties. For that, let us propose try with 8-5 bars. Then the spacing of lateral tie is minimum of, if you recall, there were three conditions. The first one is D least, because we have a square cross section, so this is 500 millimeter. Then the second option, we have 16 pi, that is the diameter of the longitudinal bar. So 16 times 25, which is equal to 400. And the last one is minimum 300 millimeter we have to provide. So based on all these options, what we conclude is that the spacing of the lateral tie is 300 millimeter. Now, we also provide clear cover of say 40 millimeter. So now the design is complete, but again we have to go for detailing. So what we have 12 number of 25 fire bars, that is the longitudinal bars, and then we have 8 phi at the rate of 300 center to center with a clear cover of 40 millimeter. So now here you can see, so this dimension is 500. Here also we have 500. Then we have main bars 12. So we have actually more bars. So let us reduce the number of bars. We have 16 here. So we have 12 pi, and then here also we have these bars, longitudinal bars here. So 12 phi 25, that is the longitudinal bars, and then clear cover of 40 millimeter. The lateral ties here we have pi 8 at the rate 300 center to center. Now, what is the distance between two bars? This distance is 500 minus 2 clear covers we have, so 2 times 40, minus we have 25, that is the diameter of the bar, divided by 2. So this is 197.5 millimeters. So here we have 197.5. 0.5 if we just ignore, so 197. And the distance between two bars here is 500 minus 2 into 40, that is 80, minus 25. So twice of this. So that is 395 millimeter. Now recall 48 times 5 is 25, is equal to 1200. So we have the spacing, which is 197 between the two longitudinal bars, which is within this 48 pi. Then now we have to provide the lateral tie. So what we'll do, we'll provide one lateral tie, which will go like this. And we will anchor it here. Then we'll provide another lateral tie, which will go like this. And then we'll anchor it here. So that completes the design process, and then we get sufficient capacity to withstand the applied load. So that completes the first example for the design of a square column. Now let us take a different example. In this example, we have a circular column. So example 2, we have circular column of length 4.5 meter. And the column is effectively held in position at both ends and restrained against rotation. That means the ends are fixed. So design it to carry an axial load designed against P is equal to P service is equal to 1500 kilonewton. And again, we design it for M30 concrete and Fe 415 steel. So let us complete the design, and for that we start with L, which is 4.5 meter, and it's a fixed column. So L effective is equal to L by 2, so 4.5 divided by 2, which is equal to 2.25 meter. Then L effective divided by D, which is a circular column. So let us assume, let us try with D equal to 450 millimeter. So we have 2.25, that is 2250 divided by 450, and this is equal to 5, which is less than 12. So we can design it as a short column. So first check is done. Now our E minimum is equal to L effective divided by 500 plus D by 30, which is equal to 2250 divided by 500 plus we have 450 divided by 30. And this is equal to 4.5 plus 15. So the first one is 15 plus 4.5, which is equal to 19.5 millimeter. And this is less than 0.05 D. Then for this case we have PU is equal to 0.4 FCK AC plus 0.67 FY times AS. So the applied load is 2250 into 10 to the power 3 is equal to 0.4 times, again we have M30 concrete, times AG minus AS plus 0.67 times 415 times AS. Now AG is equal to pi by 4 times 450 whole square. So this is equal to 1908 into this is equal to 159.11 into 10 to the power 3 millimeter square. So we can further modify this equation. It is 2250 into 10 to the power 3 is equal to 12 times we have 159.11 into 10 to the power 3 minus AS plus we have 278 AS. Therefore, we have 2250 minus 1908 into 10 to the power 3. This is equal to AS times minus 12 plus 278. So ultimately what we get, AS is equal to 341.48 into 10 to the power 3 divided by 266. And this is 1283.76 millimeter square. So let us try with 520. So the number of bars is equal to 1283.76 divided by pi by 4 into 20 square. And this is equal to 4 number of bars. But for a circular cross section, we have to provide 6 number of bars. So provide 6 number of 520 bars. Obviously, we provide more steel than what is required. So the design is okay. Now again, the last step is we have to also find out lateral ties. For that, try with five, 6, and then spacing is minimum of 3. So we have D minimum is equal to 450 millimeter. Then 16 phi is equal to 16 times 20. So that is 320 millimeter and 300 millimeter. So provide phi 6 at the rate 300 center to center. Then let us complete the detailing. For that, we have the figure here. So we provide a clear cover of 40 millimeter. Then again, here we have more bars. So let us reduce it. And then so we have 6 numbers, phi 20, and then the lateral ties we have phi 6 at the rate 300 center to center. So the detailing is complete and we design the circular column for this load of 1500 kilonewton. So you can see how we can design the column against axial compression. Now let us try another problem, and with that we'll close our discussion on the design of columns under axial load. So the last problem is again a design problem, and in this case design rectangular column of length 4 meter to carry a load of 1500 kilonewton. Column is fixed at both ends. Use again M30 and Fe 415 bars. So let us complete the design. So as per IS 456, L effective for fix is 0.65 L. So we have 0.65 into 4, which is 2.6 meter. Now let us try with 400 millimeter by 500 millimeter. Recall E minimum is equal to 20 millimeter. And in the previous class, we showed that we should have a 400 millimeter column from this minimum requirement. So let us check the other guidelines. So we have L effective divided by 500 plus d by 30. So we have 2600 divided by 500 plus least lateral dimension, that is 400 divided by 30. So this is equal to 5.2 plus 13.33, which is equal to 18.53. Now 0.05 of D, which is equal to 0.05 into least lateral dimension 400. So this is equal to 20 millimeter. So now this one is less than 0.05 D. So then we have PU is equal to 0.4 times FCK, so which is 30. Then we have 400 by 500, so AG is equal to 400 into 500, that is 20 into 10 to the power 4 millimeter square. So we have here 20 into 10 to the power 4 minus AS plus 0.67 times 415 times AS. And PU, that is the ultimate load, is nothing but 1.5 times 1500 into 10 to the power 3. So then what we have is 2250 into 10 to the power 3 is equal to, we have 2400 into 10 to the power 3 minus 12 AS plus 278 AS. So now you can see this value is actually more than what we have on the left hand side. That means if we subtract, we'll have negative on the left hand side. So let us just write that expression. So we have minus 150 into 10 to the power 3 is equal to 266 AS. Obviously, we get AS as negative. That means we need to reduce the cross section. Okay, so reduce the cross section. So instead of 400 by 500, so try with 400 by 400. Because otherwise the contribution from the concrete is sufficient enough, so we don't need additional steel. So let us try with this section. Now for this section, we have AG is equal to 16 into 10 to the power 4 millimeter square. So now if we rewrite this expression, what we have, 2250 into 10 to the power 3 is equal to 12 into, we have 16 times 10 to the power 4 minus AS plus we have 278 AS. So this time we have 2250 into 10 to the power 3 is equal to, the first term will be 16 times 12. So here we'll have 1920 into 10 to the power 3. Minus 12 is plus 278. So we'll have plus 266 AS. So effectively we have AS is equal to 330 into 10 to the power 3 divided by 266. So this value is 1240 millimeter square. So try with 520. Then the number of bars is equal to 1240 divided by 520 square by 4, and if you find it out, you'll get 3.94. And because we have a rectangular column, we can design it with 4 number of bars. So effectively we have longitudinal bars 4 number 25 bar. Then lateral ties, we have say 8 5 bar, and then the spacing is minimum of D min, in this case it is 400 millimeter, then 16 times 5, which is 20, so this is 320 millimeter, and then finally 300 millimeter. So we can provide 8 phi at the rate 300 center to center. Now let us complete the detailing. For this case, we have the rectangular column. So we have actually a square column because we have 400 by 400 ultimately. Then clear cover 40 millimeter. Main bar, we have 4 number of 520, and then this lateral ties, we have 8 5 at the rate 300 center to center. And that completes the design. So you can see how we can design columns under axial compressions, and at the end of the design what we get is the steel requirement and how we provide the longitudinal and transverse bars in the detailing. Okay. So with that, let us close here. We will stop in this week because you go through this column design for axially loaded columns only. In the following week, we will talk about columns with axial compression plus uniaxial bending. And then we will finally take the biaxial bending case. So that will be covered in the following week. Go through this 2 lectures, and if you have any doubt, please let us know. We'll clear your doubt. Thank you very much.